Let's rock this. Okay, so today I'll be talking about code pointer integrity. Paper authors are there, and some of these slides I'm going to say now are adapted from the presentation itself because they were actually really useful and probably more useful than data that we really can't see on like the paper because it's really small. So first off, we'll just go over the paper contribution. So the first thing is that it comes up with two new program properties with better security benefit to enforcement cost ratio. It's something they talk a lot about, and even during their presentation they talked about it. It's just they introduce something that's what they argue is better in terms of cost and the security benefit. So they bring forth CPI, which is code pointer integrity, and CPS, which is code pointer separation, and we'll go deeper into that later. And then next, it provides an efficient compiler-based implementation of CPI and CPS for any unmodified C/C++ code. Again, we'll talk about it later when we get to the implementation. And lastly, it's, according to the paper, the first practical and complete OS distribution with full control flow hijack protection. So protects it from any type of control flow hijack. And we'll, again, quickly go over that in a bit as well. So the problem with current implementations of...
So maybe let's first stay with the problem with control flow hijacking.
Sure. It's actually... Okay.
Yes.
So for control flow hijack attacks, they provided this nice little graph, actually, about the number of control flow hijacks, even to this day from 2004 to 2014, and the averages and the software listed there. So as you can see, IE, of course, is pretty good. IE is pretty up there, even off the graph. That's what they presented. It was actually off the graph and off the numbers. So as you can see, control flow hijack attacks are still very big, especially in the in browsers, especially IE. You can see Firefox there, and then some of the operating systems, OS X and Linux, and then and then Adobe Acrobat as well, because everyone likes to attack Adobe Acrobat. So just quickly recall what a control flow hijack attack actually is. It's just, there's just an example there with the memory on the side. So the attacker corrupts a data pointer, and then the attacker would use that to gain access to that, and then overwrite a code pointer. And then from there, the control flow is transferred to whatever shellcode that. So basically, the attacker gets you to execute their code instead of what code should have been executed. So
can you go back?
Sure.
So I had some like, they were talking about the referencing. That's when the problem, the attacker starts attacking with the whole point of dereferencing, and then they were pointing at the line 2, the second line. So what is it doing? So in first line, it is allocating memory, and in the second line, it is the input is. So this is where the queue points to the function pointer, or where the attacker wants to point. What happens at the dereferencing? That is the problem part.
So remember that we can have buffers, right? And the issue with buffers is that because you might pass in some input that's too long or something like that, you can set some value in a buffer, and it won't actually be inside that buffer, it'll instead be outside of that buffer. Right?
Okay, that's
Yes, which is what's going on here. That's exactly what's going on here.
But what happens at line 2? What happens at line 2? Why the referencing part is the attacking part?
In this case, it's because we're setting the value of something that we shouldn't be able to set.
It's happening at line 1 too.
at line 1, we're getting an address. We're not playing with some points in memory that we shouldn't be, right? So we can compute pointers, and those pointers can point anywhere, and that's okay if we never use them. As soon as we use a pointer to something inappropriate,
And that's inappropriate because the attacker can replace input 2 with.
so it's because Q points to something that it should not, and the attacker has control of input 2 and can make it, can store inside that whatever it wants.
So it basically point to the function pointer, and then that would point to the shell code.
Right. Right.
So input 2 would be
It
function
would,
pointer?
yeah, it would look at that, and then that would look at the shell code, and then it would execute the shell code, which would give them.
Okay, so input 2 would point that function.
Yes. Yeah. And it just so happens that you can store that in some position that happens to be a function pointer when the program thinks it's just setting some safe variable inside a buffer.
And how does the attacker get access to corrupt data file?
That's the buffer overflow.
I mean, giving input?
Yeah, just
So basically, it just goes past the
Do you know how to
buffer,
make
and
this
then it
type
points
of
here
attacks?
instead,
Is it possible
like
for
in
you
the
to
buffer where it's
demonstrate
safe.
this in vivo? I would love to see.
So I would have to set some stuff up first. It's not that hard to do these types of attacks. But if you want to see some videos, the AEG paper that we looked at, they have some videos online that show them doing these attacks.
Well, I saw lots of videos and stuff, but I wanted to kind of see like in vivo, like on a truth.
Really, in the paper that he presented, right?
Yeah.
So they were a demo of a code that, like you, through the input you can pass them. Oh, I see.
Yeah. And
Because I'd like to see it too.
it's not that hard to make a contrived example. Doing it in the real world is much harder.
Contrived to
We could come up with one. We'll have some. We might have some more time. Not this coming Thursday, but the following Thursday, maybe. If so, we can work through that.
That would be good. In fact, it would be interesting if course will teach us how to do this, so we can examine that.
If it was that easy, like.
Google money?
Yeah, I'm afraid of
That's
it.
better than a blackmail route. Okay.
Okay, so some of the problem with current implementations is that they can't guarantee protection against control flow hijacks while having a low overhead. And some of the approaches are just listed here: DEP, which is data execution prevention; ROP, which is return-oriented programming; and ASLR, which is address space layout randomization. So for memory safety, it's something that's already currently used in a lot of things to prevent control flow hijacks. For example, in interpreted languages like Python, Java, Swift, as listed here. But the problem with that is that memory safe programs themselves still rely on C and C++, and by default that's not memory safe. So just a small example that they had was that in 3,000 lines of Python code, you'd execute about 500,000 lines of C in the Python runtime, and libc, which has about, as you can see, 2,500,000 lines of code of C. So in terms of memory safety can be retrofitted to C and C++, but then it provides, yes, go ahead.
I have a question on the previous slide.
Sure.
So how does Java and C# prevent these? I mean, their virtual machines take care of the pointer allocation and everything?
So every time you, for instance, try to access an element inside an array in Java, what happens?
Checks to make sure that that element is inside the array.
Checks to make sure it's in bounds.
There is also another, that's because he didn't explain the memory safety stuff. It's the dangling points
dangling
and
pointers.
the
Sure.
out of bound
Yeah.
memory access, which is when you access an index in an array that is out of bound. So Java, you don't have to care about the dangling points.
So what do you worry about dangling pointers in Java?
Move pointer, etc.
We don't do the garbage collector takes care of it.
Right, all memory management is automated. So the stuff is there until the pointer is null. And once the pointer is null, you get a null pointer exception anyway.
Right.
So,
So, can you create a control flow hack from anything like on modern computers, on anything besides C and C++?
yes. Any low-level language, in theory, unless it has, extra checks in there to specifically guard and create memory safety, has at least a window.
Yeah, I guess in assembly, yeah, of course you can.
I mean, there are attacks, for instance, against the Java runtime.
Oh, okay.
So this is why this is relevant, right? Because if you rely on this runtime, well, the runtime itself might not be safe. So if you can correct the runtime, then this is just another avenue of attack. The original Java program or Python program could be totally safe, but the runtime itself that you rely on, maybe not.
Okay, so in terms of memory safety, you can implement it, but most of it has overheads and trade-offs. So, for example, with softbound and CVTS, you can see the percentage of overhead that they give, and then a lot of the other ones, they either require language modifications or hardware modifications, so it requires a lot of additional work, and it requires a programmer to change how they code as well. So, in terms of instrumenting memory safety, this was just how they placed it in terms of first assigning metadata to it, and then you propagate the metadata, and then you make sure to check the metadata. So that's why it has a lot of performance overhead, because you have to do all these checks every single time.
So what is that metadata? Any hypotheses?
From what I understand, isn't it just additional data based on what is held inside and where it can be, like the bounds within?
Right. So it's just a range of the valid targets for this thing, based on what you're getting this pointer from. Yeah.
I've always wondered, is metadata just similar to like shadow data where it
Yes,
just
absolutely. That's it. It's data about data.
So what do you mean by everything? You said they assign metadata for everything.
For everything, I mean just for mostly pointers, anything that requires to use memory, that's what you keep track of metadata for.
So with every pointer access, you've got another access that either checks this metadata or transfers metadata from one place to another.
Every pointer access, right? So, but they were saying that they do it only for.
But this is the older approaches.
This is for
So
memory
they said
safety.
this approach covers more than what they do, and they only do it for code pointers.
Yep.
Then what's the difference between code pointers and all the other pointers?
I'll get into that when we talk about CPF. This is just the older approaches where they look at all the memory, and every single pointer would require metadata, and that's why the overhead is huge in comparison.
Soon gonna be exploits that will exploit the programs with the metadata. They will exploit metadata.
Ideally, you isolate the metadata.
Yeah.
But we'll see. We'll see.
So the question is, how do we deal with this? Because it's not practical for us to use memory safety because of the overhead. Right? You don't want to have to keep track of metadata for every single pointer that you ever use. The overhead is just not realistic, and some of the implementations we saw earlier also required you to have hardware level stuff or software level changes, and that's also not practical in the long run. So the first thing is we have to look at how to make control flow hijacks impossible. So we have to guarantee the integrity of code pointers, which are any pointers that point to code, and we'll talk about that a little bit more as we go along. And next, this leads us into our topic today, which is CPI, which is code pointer integrity, and CPS, which is code pointer separation. And we'll talk about the differences of that as we move on. And then the first thing that we will look at is talking about splitting the process memory into something we call the safe region, which is where any code pointers will point to in terms of we know this memory is safe and it can't be attacked, and then the regular region. And then we'll use type-based static analysis to find instructions that access code pointers. Okay, so first we'll just look at code pointer separation. Is there a question?
Oh, no, there will be.
Okay. So first we'll just look at the memory layout for code pointer separation, which is talked about later in the paper, but we'll go over it first because it's just a subset of CPI basically. So in terms of safe memory, we look at the code pointers. So we see there's a safe heap and the safe stack, which we'll talk about again. So any instructions that operate on code pointers can access the safe memory, and everything else should really only access the regular memory so that there's no way for them to basically just modify what should be executed. They can only change, at this point, only change what code pointer is pointed to. So there's also a hardware-based instruction level isolation between the two memories, so they can't just, like you were basically saying before, like look at the metadata or just try and attack the safe memory, so it's hidden from them to some degree. So first we'll look at the heap for code pointer separation. So as you can see in the code there, the function pointer is stored in our safe memory, and that's where our code pointers are held, such that it's isolated from our regular memory, where all of the non-code pointer data is stored. This way we don't need to keep metadata, like with memory safety, where we have to keep metadata of everything, because we guarantee that only the code pointers are found in the safe memory. So because it's isolated already, we don't need to deal with every single one keeping track of metadata, where it is, what the range is. And any of these instructions that access code pointers are identified, again, using type-based static analysis. And of course, separation enforced by hardware. And this means that our regular memory, the memory layout, is not changed. It's only that the code pointer is stored on our safe memory instead of on our regular memory.
So the safe memory, is it something really similar to address sanitization, or is it the same thing?
Address what?
Address sanitization?
So I think you're referring to the address sanitizer work that we looked at earlier.
Right.
Can you clarify?
Then also there was a concept of there were safe areas of memory that you can access. Anything outside is poisonous.
Okay. There's a shadow. I guess you could look at it that way. I mean, you do have.
What's that? That was called some, what was that called?
Address sanitizer.
Yeah, so we looked at the address sanitizer tool earlier when we talked about dynamic
What's
analysis.
it sanitizer?
I wouldn't say they're tightly related. I'd say some of the core tools of implementation are related.
So one thing I don't understand, so the function pointer is the code pointer. The function pointer, the rest are not. But I couldn't find, like in Google, the definition of a code pointer, but I couldn't find a definition for a code pointer. So I don't know exactly what's a code pointer.
Thoughts?
So any kind of pointer which is like a return address would be a code pointer, and code pointers put any kind of sensitive data which we might want to protect.
Okay, I would say they're more restrictive than that. There could be sensitive data that they don't protect, although they do say you could extend it to protect any type of sensitive data. But their version is, in theory, a pointer that points to code. As simple as that might be. Right? What kind of code? Anything in the text area. It might be enough. You could over approximate it that way.
Anything which a user can manipulate basically.
Well, you usually could manipulate other sensitive things. So if you have a pointer that tells you what instructions are going to be executed, that is a code pointer, right? So if you have a function pointer, that is a code pointer. If you have a dynamically selected address of a goto, that is a code pointer. It's one of the other common areas. And oftentimes, function calls can actually be transformed into direct gotos to a particular address inside your code, in which case, that's a code pointer. But return, right, the return address is also something that tells you, well, okay, go to this point in the code. So that's why that's a code pointer. It's just a pointer that represents instructions.
So it's not mouse pointer pointing to C++.
Not in this case.
Don't all pointers point to? Then why don't we protect all of them?
Well, because you can have pointers to data, things that are just data. Right? Maybe I've got a pointer to a big buffer of integers.
Oh, then so this approach, can they extend using this approach for data attacks? I don't know.
Their point is that they don't need to, right? You can guard the code pointer stuff and guarantee that you don't have, at least under their attack model, under their definitions and so forth.
They're subset of.
Right. You've got to be careful about the legalese here. Under their assumptions, you can guarantee that you can't get control flow hijacks. And you can do so with decent efficiency. If you guarded the data as well, you would suffer from guarding additional instructions, additional operations, and higher overhead, higher runtime overhead.
Because they were really just aiming for low overhead.
Yeah. They want something that you could use on code as it's deployed in the wild.
So next up, then we'll just look at the stack. So for the same thing, stacks are also separated between the safe memory and the non-safe memory.
Let's actually go back on one slide for one more point I remember that I wanted to bring out. Down here you say memory layout unchanged. Why?
So basically, from what I understood from reading the paper at least, is that the memory layout is unchanged. That part of memory is just not, it's just not used. It's either used on the safe side or it's used on the regular memory side.
Okay.
So they would never be pointing to the same thing, and they would never be used at the same time. So for example, when we talk about CPI later, there might be a time when a pointer is safe and it needs to be on the safe memory side because it's a code pointer. But later it could point to just an integer, in which case it could be stored in regular memory instead.
So, am I understand correctly? That means if we have 2 gigabytes of memory, on 1 gigabyte will go for this safe memory, and 1 gigabyte will go for regular memory. But safe memory, this 1 gigabyte will be used only 2.5% of the time.
Okay. In theory, what you're saying is true. What about modern memory management means that it isn't true?
Trivia question.
That you probably encountered inside your operating system's classes.
You can use
Agent?
You've got virtual memory. You have virtual memory. So even though, yeah, you're saying that you're only using a certain amount of it, well, you're not actually using the rest of that reserved space anyway. You have this virtually reserved space of, maybe even 2 gigs. Doesn't matter. You can have a larger address space than you got physical memory. That doesn't matter. That's okay. But you just got this extra shadowing going on. That's like a second set of virtual pages that can only be accessed by the state instructions. You can look at it that way.
But still it has more memory overhead.
You will have memory overhead.
And they don't talk about it, right? They don't talk about more memory overhead in the benchmarks.
Not a whole lot.
Is it because they really have memory overhead?
The memory overhead for a technique like this should be marginal. Should be. We can talk about that.
Did you say that it's negligible?
And this makes sense if, most of your operations don't actually deal with these sorts of these difficult memory accesses. And so most of your data doesn't have to go into that safe area, which means that you don't actually reserve memory for it. Let's move on and come back to this.
Okay, so next up is just looking at a stack, where they, again, separate between a safe stack and a regular stack. It's just something they talked about in the paper, just for their implementation's sake. They implemented something called the safe stack, which is basically the same idea with the memory, but instead looking at stacks. For them, it just made sense to instrument it as a different thing. Also using the same tools. So basically, all locals that just make sure that the safe stack side is anything with to do with code, and all the accesses on that side are safe. And for regular stack, it's anything regularly used. And honestly, they even said the stack isn't even used all that often, the regular stack, but it's mostly the safe stack, because most of the time you're doing things that are vulnerable to attack, so most of the time it would be on the safe stack.
Okay, so let's take a look at what's actually in the safe stack. Based on their example function, what's in there? Okay, what's R?
Some input.
Well, ours is just an integer. It doesn't matter the semantics of it, just the raw data there. It's an integer. The return address is also there. What's in the regular stack? The buffer. So only things that could be dangerous ever go into the regular stack, right? So if you don't have anything that's dangerous, you don't have a regular stack. That's why we've got this nice justification. And we don't even have the extra shadowing issues anymore, because we don't have to worry about where R is relative to buff inside a well-formed program. So we only ever need an extra regular stack if we have some sensitive stuff or some risky stuff, and there aren't any gaps in here to maintain the layout.
It was not clear to me, what is the technology again?
In this context, there's some other subtleties because they're not really describing the implementation details quite so much. Neither of these is a shadow. These are each separate, independent, fully valid, but serving different purposes, views of memory. A shadow, in their case, would be what they use to maintain the metadata. They don't talk about a whole lot. But do people see this notion that, okay, you can have your safe stack, it has something like an integer, because you can't overflow an integer by itself, right? So you can have an integer, you can have return address, everything in there that's safe, but then the idea is, okay, you got a buffer? Well, accessing a buffer could be unsafe, so just put it somewhere else. And that way, if you try and access the buffer, there's no way overflowing that buffer is going to affect your safe stack. That make sense?
Like the buffer is not related to the return address, so.
Yeah. Just allocate some chunk of memory somewhere, put it there. That's all it is.
And put it somewhere where it can't access the other memory.
Mm-hmm. Right. Yeah.
Okay, so under CPS, the only thing it promises is that an attacker cannot forge a code pointer, so they just can't do anything on the safe side in terms of putting code there. They can't inject any code, but what they can do is what they can do under CPS is make you look at a different code pointer, but they can't write the code pointer themselves, but they can make you do another operation that you didn't mean to do, from what I understand.
Yeah, I agree with your explanation. Do people understand that explanation? It's a little bit subtle. This might be a good use of markers. Because I do have
I was
markers.
really hoping for a drum roll.
A drum roll?
Something really special.
I'm not going to say cookies. Cookies will not help this situation.
That would have been much better.
Shall I?
That's awesome. Okay, so where should I start with this example? I guess.
Maybe show first what they can't do with CPS.
Okay.
Which,
Maybe you can go back to the example.
draw a chunk of memory and just have a code pointer in it.
So let's say we have a chunk of memory here,
Fine chunk of memory.
and then let's say here we have some code pointer.
Mhm.
Anyone have a name or anything?
Happy with the name? Yeah.
886.
Foo,
Yeah, all of those sound fine to me.
that's a few.
So is it regular
Call it
memory?
K.
This is the what?
Okay, so let's say this is a function pointer and maybe it points to food or something like that.
Okay.
What can they not do with CPS?
So under CPS, what they can't do is basically overwrite anything here. So they wouldn't be able to overwrite foo with their own
Shit.
bomb
Okay.
or whatever.
What can they do with CPS then? This might require drawing another chunk of memory.
Okay. So let's say here.
Yep, I think you're on the right track. You were about to draw
Like a
another
point
code pointer, right?
Go to their code.
I guess let's say there's like a bar or something here. Well, if that helps. Isn't it basically they can make from over here instead of pointing to foo, make it point to bar, so you access bar instead of foo?
Nope, not quite. Depends on the semantics of what your diagram means, which is a little unfair. I would look at it a little bit different. I would draw another little thing down at the bottom. I would say, instead of having bar right here, let's put bar over here. Right? And then maybe I've got P in here. And P points to this. And because of the wonderful Machiavellian tactics of our attacker, they decide to cut this and make it point over here instead. They've changed the data pointer. But changing the data pointer affects what you'll call if you indirectly access bar. Was that remotely clear?
No.
Yeah, I'm seeing a lot of blank faces.
How can a data pointer affect the control?
Aha, because if you change this data pointer, then later on, when you decide to look at a field inside this object, one of these fields is a code pointer, and you'll use that code pointer and go somewhere wrong. Right?
But it's a data, it's not a code pointer.
This is bar. This is a code pointer.
Okay.
Right? So let's say, for instance, that these are maintaining, we've got some implementation of object-oriented design in here. So this is like a virtual pointer or something like that, So you're pointing to one object, and this object has its table set up such that calling through this pointer calls foo.
Okay, so the data pointer would be talking to object A.
Yeah,
And then
you
say,
make it
no,
talk to
no,
B.
Talk to B, and then B executes instead of A.
Yeah, so it's you can think of it as being like polymorphism, and you're using the wrong type. So instead of calling foo, because you changed what this pointer pointed to, you end up calling bar through this indirection. Is that clear?
Is it basically copying the whole thing? Or?
It's not a copy. It's not a copy. It's just you change what P points to,
Okay.
and because it's no longer pointing to this object that had a function pointer, it's pointing to a different object that has a different function
So these
pointer.
are objects and not memories, right? That's what you're trying to say. You call it a memory chunk, right?
Yes.
Now you're saying that it points to a different object, so the object is inside the memory.
There's no difference between the two. An object and a memory chunk, synonymous. Doesn't matter. It just so happens, here's, let's say this is a struct, and this is a field inside that struct,
Right.
that is a function pointer.
Right.
This is a different struct.
Which with the attacker.
Yeah, the attacker, well, maybe the attacker didn't even create this. In fact, they couldn't, because we've got safety there. Maybe this was created for a different purpose.
And they just look at something else.
Yeah,
instead.
so essentially, maybe there are valid reasons to call bar, but because you're calling it at the wrong time. They're making the program call bar when it didn't expect to. In fact, this is the most common way to do attacks, except kind of, not exactly like this, but through something called return-oriented programming, where you change the return pointer to point to something else that's valid, but not valid at that time.
So like maybe deleting an entry instead of adding an entry?
Sure. Which if we spent longer talking about things like return-oriented programming and gadget construction, and all these wonderful pathological techniques, which you could spend a whole semester on, but we didn't, then that would be a little clearer. Would people get that notion? There's an indirection there.
You should definitely spend your next class just being, all right, this is how we hack.
It's interesting stuff, and there's a lot of money in how we hack, but
That's what you should teach us.
Which I guess you basically are, because you've taught us how to find bugs.
and how to exploit them.
And how to exploit them, and so where to find them. Okay, that's what we taught. Bugs are exploits, so how to take advantage of those. Okay, it's kind of just
I just haven't focused on here's how you implement something to blackmail, these foreign dignitaries or something like that.
See, that's the
We can come up with this on our own, like, we are grass-rooted after
But
all.
aren't most of these bugs and exploits which we are seeing are related to C and C++? How do we do it in Java?
You would attack the Java virtual machine.
The runtime.
Yeah, you'd attack the runtime part.
And so if you have an exploit to some part of the runtime, that means you have exploit to all the Java program.
I feel like the Java run is
Can
getting
you
pretty
go back
secure.
to that?
Oh, okay.
Relatively, maybe, but relative to what?
C and C++. Really? I always thought Java would be secure. It's built sooner. Okay, fine.
So we're just going back. They actually had an example for it.
Okay.
Yeah. So we've been over this. So basically, I don't need to go over this again, do I? Is this clear?
Would it help?
Would it help? Would this example help?
Would make a difference though.
Practice, yes. Yeah, that's like that. You go ahead. Go to.
Okay. So basically, the step-by-step is that the attacker would corrupt a data pointer at some point. So say this one here, and then it would use it to corrupt the structure pointer in this area, and then program would load a function pointer from the wrong location in the safe memory. So instead of say picking the valid function, it would pick something else. And then the control flow is transferred to a different function whose address was previously stored in the safe memory. So it just do something else other than what was actually intended.
Could you explain from the code what is related to this? For example, yeah, just say what happens at one, then yeah.
Okay, so for this example, you see how in point one, we create the integer pointer there. And then, so step one, Q would be here. I'm actually a little lost.
The description below
Yeah.
is
Okay, so one, so you set Q to be there where the structure pointer is. And then for two, it would corrupt the structure pointer somehow, like getting it to overflow or
point to the wrong.
point to the
structure.
wrong thing. And then from there, it would it would then point to here.
Yeah.
And then from here, it would pick a different valid function instead of the one you were actually
If
looking
we
for.
look at this memory layout, we can see two different objects, right? There's one with a function pointer up at the top, and there's another with a function pointer in the middle, like func1 pointer, right? So all we're doing is changing Q to point to one of these objects instead of the other. That's it. That's it. Nothing more complex.
So how do we change Q? It's like just adding with the input? Is it?
Buffer overflow? Yeah. So I mean, they oversimplified it a little bit, but basically, if you got some input, it can affect the value. Let's say through a buffer overflow or something else. They oversimplified that part in the slides, but basically, the user input, whatever it is, can affect the pointer, is what they're saying. So they're just over approximating that.
Okay, but we do have that line of code, right? It
Yeah,
is
yeah.
instrumented.
They're saying that happens in one.
Okay.
So now we look at CPI. So under CPS, of course, they're able to move what function you're supposed to use. Under CPI, you protect all sensitive pointers, and the sensitive pointer definition is actually recursive. It's all code pointers and pointers that are used to access sensitive pointers. So basically anything that uses a code pointer or can later use a code pointer or stores a code pointer becomes a sensitive pointer. Therefore, if you protect that, there's no way that they can actually make you go to function pointer down here, because that's in safe memory as well.
Right. So the difference here is what? What else is protected in this case that prevents the bug?
The struct pointer?
Exactly. So because we protect the struct pointer as well, because we have this recursive definition, we can't change what object is being pointed to, and it stays safe. Seem reasonable enough?
Okay, so again, we protect all the sensitive pointers, and of course this definition is recursive. And again, splitting the memory regions. And CPI identifies all the sensitive pointers using an over-approximate type-based static analysis. And the code of this is there. And
I will say that it's more subtle than they present it, because that's hard. That's a really hard thing to do, and they don't discuss it at all in the paper.
Yeah, they don't actually talk about how they really implement it. They only talk about what they use to implement it for the majority of the paper, and we'll summarize
Which
it.
is something you can do to a security audience. If you present the same paper to a program analysis audience, just like we talked a little bit before, how the audience matters, you present the same paper to a program analysis audience and it'll get killed because they don't present the actual analysis. They just present how it got used to solve the security problem. It's kind of interesting.
Where was this published?
Units.
2014, 6
Yeah.
months ago.
Oh no, it was in ASCII. Operating system design and implementation. But still Unix, which is more pragmatic.
So
But they have the source code, so if they have.
Oh yeah,
that's source code.
they're actively working on getting it into Clang. Yeah, they've been working for a little while because there's some complications, but yeah, I mean it's very much open.
So if they get it into Clang, then the pointers will be more stable.
I mean, yeah, in theory, if you compile with this enabled,
Less time.
hopefully.
Then there will be assignment 4.
Then there will be.
Assignment 3 wasn't as difficult as this, as much as it might seem like that. Anyway, yeah.
So the over-approximation doesn't actually hurt the security portion, but it does affect performance because you have to do more and protect more. Basically, you just have to keep track of more things in safe memory.
Yeah.
So the code pointer integrity in terms of memory layout, it's basically the same thing, except we just add in the extra pointer that we talked about earlier. So in terms of the instruction level isolation, they talked about this as well. They just, I was actually a little confused about this question, to be honest, in
Yeah.
how they talked about how they use like registers.
This is a low-level systems aspect.
Yeah.
Yeah. So depending on what type of architecture you're working on, you're going to have different benefits or options here. If you're working on a 32-bit architecture, then you can use segments, and you've got this hardware-based isolation. That's nice. If you're not, then you don't have those segments, and you don't have some strict hardware-based isolation. You basically put your safe memory at a random location.
And hope they can't access it.
Oh, is this to separate the address space?
Yeah, you want to separate the regular memory from the safe memory so that, you know, if there's corruption in the regular memory, it just affects the data instead of the code pointers. And if you keep them, you know, with a 48-bit address space to work with, where you can actually move things around, there's a fair argument that if they did corrupt the regular memory, they'd crash the program before they ever got to the safe memory. This is true, but yeah, it's obfuscation based to some degree.
So they just basically hide it somewhere else in 64-bit and hope that the software crashes before they can find it.
It's a little bit more than hope, but hope, yeah, sure.
Hope with good reason to hope.
Yeah.
So just a comparison of CPS and CPI again, it's just we add in any sensitive pointers, so any indirect pointers that eventually point to sensitive pointers. So it doesn't have to be right at the offset, or it's any time it can point at the code pointer. So that's why we use static analysis to actually look through the whole program to see if at some point maybe a pointer that just points to an integer for most of it eventually points to a code pointer.
Yeah.
And then accessing the sensitive pointers, we make sure it's safe. So we also have to add on runtime checks. So when it runs, we might not know, and it might eventually become a sensitive pointer, and we have to store it in the safe memory instead of the regular memory, because it becomes a code pointer instead, or a sensitive pointer.
How did that happen? Any ideas?
How can unsensitive pointer be objective?
Yeah. Well, what does it mean if it's unsensitive? We'll start there. Because if you got to change from unsensitive to sensitive, you got to start out as unsensitive. So what does it mean if it's unsensitive to start with?
The code pointer or something that might point.
It's just
Or
pointing to
points
the
to a
data.
code pointer.
Okay. If it's starting as sensitive, it just points to data. That's exactly right. So you got something, maybe it's a void pointer, and it points to some integers. Right? And so how does it become unsafe?
Because void can point to anything.
Yeah, you assign something that's a code pointer to it. That's it. And so it's just this dynamic check, so you can adapt on the fly. That's it. Okay.
I guess that they covered it earlier, that sensitive is a code pointer or something that could potentially point to.
Right. The issue though is that before they talked about identifying it statically. And the extra risk is that you can say, well, now we have to worry about dynamically figuring out whether or not it's a code pointer or a data pointer. So you got these runtime checks.
So then they basically talked about in this next table how secure and each of these techniques are, and the average overhead. And there were some questions about this later on. During their presentation, there was questions about their overhead numbers. But so basically, you can see memory safety, the security guarantees are precise. So it's impossible basically for you to do this one specific attack of memory hijacking. So the average overhead is about 116%, not practical. And then the CPI, which is the guaranteed protection, it has an 8.4 to 10.5% overhead, while CPS, which is more practical, only has a 0.5 to 1.9% average overhead. And then they talked about finest grained CFI and coarse grained CFI, and there were some questions about that. What I understand. I don't actually really understand that, when they asked the CFI question.
That's because CFI was kind of the initial work that talked about control flow integrity in general. And we didn't really discuss that too much. This was a previous existing technique which basically said that if you are going to have an indirect jump somewhere, that somewhere is a valid target. Now, the thing is that it might be a valid target for some other part of your program, but not a valid target for this particular part of your program. And it's difficult to make that guarantee precisely. So for instance, how easy was it to make a precise call graph so that you know exactly which function was being called at a particular point?
Extremely difficult.
Right. In fact, maybe impossible to do perfectly. Right? With static information. And so, without that information, you don't know which calls are valid targets and which aren't. And so it's difficult to protect for. And you know, the ideas that CPI and TPS are a little bit better on those potential vectors.
So CFI will, the only drawback of CFI is that it does block control flow out, but you can still take control by pointing to something else in the code. That's the only thing you're allowed to do is move the pointer to something else in their original code. The unfortunate part is you can actually still move it.
Sure. I mean, there are some other issues that come up because of approximations they make just to make their system work at all in practice.
Okay.
Or efficiently. That make it so that you could actually set a pointer. But what you set that pointer to would maybe be a conservatively possible target, but not an actually possible target. And the distinction between those two opens up an avenue for attack.
Okay.
Yeah, because you don't have precise information. You know, statically you just don't have precise information.
Does CFI not use any dynamic information?
No, it's entirely static.
Okay.
So let's. I think we're just about at the end, right? Probably some overhead information,
Yeah.
but you know, you heard over and over. Oh, we've got roughly low overhead. There was some debate about that. Does this mean that if I were an attacker, that I could not alter the control flow of the program? Is that what they're saying?
Well, no, you can just run the program. Running the program.
Okay, let's say in an unintentional way. Do they provide that guarantee? So what are they doing? They are controlling these code pointers, right? So I can never corrupt a code pointer. Let's even take that for granted. Let's say that they are doing exactly what they say. There's no flaw in their underlying assumptions or logic. So I cannot affect my code pointers. Can I still hijack the control flow in some way?
They seem to think not.
Do they? Or are they just careful about their presentation?
But they say they cover all kinds of control.
You can't take control flow through pointer manipulation.
Okay, you can't take control of the control flow through pointer manipulation.
How else can you take control flow without pointer manipulation?
How else could you affect this unintentionally? Any thoughts?
Does changing data do anything?
Okay, does changing data do anything? This is the right direction. Like these are the kinds of questions you should ask yourself with these sorts of things, right? So can we come up with some way of, corrupting, let's say, the behavior of a program just by affecting the data?
Yeah, just like check the conditions. They may have overflow too, so the
Okay.
overflow.
Yeah, so we could have a buffer overflow that doesn't change a code pointer. It changes some data somewhere. And that data could be used in a condition. And then will still affect the control flow. Not in the same way, right? The way in which we can affect the control flow is severely limited because we can't,
You can't hijack it.
Right.
You only change an if statement.
we can't force it to go to arbitrary shellcode of our choice.
Yeah.
We can just change the outcome at a particular location. Now, maybe doing that particular change of the outcome at a location cascades into some other errors, and those other errors cascade into more errors that eventually let us get some control in a way they didn't expect. That kind of thing is possible. I'm not sure exactly how. It would be very program dependent. It's not a generalizable thing, but it means this isn't a be-all solution for preventing all attacks ever. Your program is not
But they do still.
a substantial number, and they make it a lot harder. They raise the barriers. They increase the cost of taking control of a program. Dramatically.
Still a hard time.
Well, let's say, okay,
How can you gain control flow
well, it's not,
without?
just think about it as corrupting, right? And the question is, what are the potential outcomes of that corruption?
Oh, no,
And that's
no.
what's unclear.
But they just the task of gaining control flow.
Okay,
Like that's the only thing. Can you gain control flow if this is implemented?
yes, yes, not through code pointers. So let's say I've got one buffer here, and I've got another buffer inside my regular memory here. One buffer after another, right? I exploit a buffer overflow on this buffer, and as a result, I'm able to write some value into this buffer. A condition computed based on the values of this buffer might force me to take then the true branch instead of the false branch, which I would have if I hadn't written that value. And thus I will change the control flow.
I didn't hijack the control flow though. I don't get to write anything back. I'm not
You don't
controlling
get-
the program.
You don't get to point, well, it depends.
I
You
don't
don't
get
get
to
to point it to
execute-
your shell code directly.
Yes.
But you
This is
might,
true.
you just hope you might end up there.
Yeah, the question is, does this cascade? Is there something else further on? Or is this enough? In some cases, this might be enough.
But then you would have to rely on
It's a deeper,
you would have to rely
Yes.
on the programmer putting something into their code directly that allows you to gain control.
so let me put it this way. There's a technique called return-oriented programming. And the idea is that if you're able to overwrite the return pointers, essentially, right, on the stack, then you can make them go to some existing code. And they don't add any new shell code a lot of the time. Instead, what they do is have that return pointer point to something in libc. And there is a proof that pointing to things in libc gives you Turing complete capabilities. So you can have that do anything you want.
Okay.
Now the question is whether or not you're able to leverage this sidetrack into unexpected behavior that can give you similar capabilities. It's a lot harder. It's a lot harder.
I guess if that decision was password fail or like accept password and log in or reject
Then
password.
letters. Yeah. So it's difficult to say. By itself, you're right. That is not enough information to say, hey, I've got something I can exploit.
Yeah.
It depends on what it changed together. But even in those issues we saw in Kansas West, right, where the guy got $250,000, he chained multiple exploits together to get those. So that's pragmatic. That's not unreasonable.
Data bit attack? Data bit attack? What is it? Data bit attack? Bit data attack?
Big data attack?
Not big data. What is something called data? So is it called data attack? Or something called data?
It depends on what you're looking for. You are in a sense attacking data. I mean, you could look at data leaks maybe this way.
Oh, data leak attack.
Okay, yes. This is one potential avenue for creating a data leak, information leakage. Yes.
So data leak attack is actually the buffer flow.
You could cause one that way,
Data leak attack would just be anything where,
a leak of sensitive information.
so like,
So that's the thing.
they print out the password.
You could leverage it into one. So let's say that you change one of these things from being true to being false or something like that, and as a result, you print out a credit card number.
So, but they say that they don't cover data leak attack. I mean.
This is true, but that's not the only thing that this could do. We don't know what changing the control flow here actually does. It depends on the program. So it's not a generalizable concept. The issue is that this change would have to propagate down and cascade into a series of other issues in order to have a dangerous impact. But that does happen in practice. So this doesn't make your program rock solid. It just makes things much more secure. And ultimately, that's what it's all about. you should realize you're never going to have something that is absolutely secure. If you think that is the case, you're horribly, horribly mistaken and putting yourself at risk. It's all about raising the barriers to make, it's like the old adage of, if you run across a bear in the woods, you don't have to be fast enough to outrun the bear, you just have to be faster than the other people around you.
Just have to be smarter than you are.
Yeah.
Yeah.
Right? Because then they'll get attacked instead. So it's the same thing.
So what that is you just have to be more secure than the next program.
Yes.
So that somebody else gets hacked, not you.
This is true.
Okay.
And so you take this into your risk assessment. What is the value of your data, and how much effort are people willing to spend to get your data or to attack your system, and then have enough barriers to be high to have greater prevention in comparison to people who have comparative value data.
So a business proposition for you then would be to create a company that has really bad security, because that makes everybody else's job easier because they don't have to outrun. It's
And
like
why
bringing a
would you
slow
do
person
that?
along an
What
island.
kind of
Time to live in this company before somebody would look at it, It would be close to zero.